of Colorado. Rafael specializes in control and processing of optical radiation at two significant spatial and temporal scales, the nanometer and femtosecond. And he's looking at applications in new devices and systems. And so he's doing computational optical sensing and imaging. And remember, this morning Kishan was talking about particle tracking. I think we'll hear more about it from Rafael tomorrow, is it?
Maybe.
Yeah.
Thank you. Is the microphone?
It's not on.
Can you hear me in the back?
Yeah. Also,
Okay.
On or
There's probably a board or something. Okay, I would like to thank the organizers, Alina and Ivan, for inviting me here. This is a very exciting workshop. Unfortunately, I couldn't attend the first 2 weeks. But I've seen the quality of the talks today. It's very impressive. I want to talk about this topic of super resolution, which has been one of the hot topics in imaging in the last couple of years. And so, and I've been presenting some review of different techniques and then things we've been doing in this direction. So I'm going to talk about diffraction limited imaging, the resolution limit, and I apologize if this is a repetition. I'm assuming most of you know about this resolution limit, and then discuss whether it's possible to do imaging beyond the diffraction limit. And here we are talking about overcoming the half wavelength, not just the numerical aperture limit, but going far beyond the wavelength, and see if that's possible. And then I'm going to talk about cones in 3 dimensions and how to we use techniques called computational optical imaging, essentially digital processing combined with optical design, so to get more information from a system. Okay, so what is the problem here? When the reason why we cannot see the stars closer, like with the Hubble telescope, is diffraction. Yeah, and diffraction, what I guess all of you know, happens when we have an aperture. You get waves that diffract into the edges, and the smaller the aperture, the wider these waves are going to expand. And so in an imaging system, if we have a point source, something really small that emits light, we are going to see a blur. Okay? And this blur is called the point spread function. If you have 2 point sources, then you have 2 blurs, and if the 2 point sources are far apart, you see 2 blurs. You can distinguish where they come from. Now, as these 2 become closer and closer, the blurs overlap, and you might have a problem at some point. Clearly, you have a problem separating these 2 sources. And so there are different criteria to establish what is the resolution, and there's a rating criteria. But ultimately, it's going to be somehow some quantity that depends on the numerical aperture, essentially the cone of light that the optical system can accept. Okay, so if you can accept wider cones of light, you're going to have a thinner, narrow blur, and so you could distinguish sources that are closer. Ultimately, I have to say, this depends on the noise that is present in the system. If there were no noise, you could always separate 2 points. Now, so you get a resolution that depends on the wavelength and the numerical aperture. So the higher the numerical aperture, the smaller the spot size, the better the wavelength. So in the transverse direction, this microscopy is to about 200 nanometers in the resolution for the imaging. And a similar situation occurs in Z, in the axial direction. You can resolve objects that are very close, but not more than about this number, which also has lambda, the numerator, but the numerical aperture square in the denominator. And we have the index of the refraction of the medium. In microscopy, we use oil or water, so the index is relevant there. So in the Z direction, this is about, say, 400 nanometers, typical, kind of the best you could do classically to resolve. There are ways of improving this somehow, using, for example, confocal microscopy, but these are minimal improvements. There's an alternative view of this. As you probably know, if you make a cross-section of this Fluorescence function, you get something like that. And if you perform a Fourier transform, you get the frequency response of the system. Okay, so the frequency response here is representing only the modulo of the frequency response, which is called the modulation transfer function. And essentially you can, instead of giving the resolution, you give a cutoff frequency for a system. And what does it mean? The modulation transfer function means that different frequencies, okay, low frequencies, like this rating, will go through with a good contrast, but high frequencies, somewhere here, like this one, will go through but with a very low contrast. Okay, so high contrast, low contrast, at some point they don't go through, so you don't get zero contrast. So that's after the cutoff. And mathematically, this relationship is very simple. It's just if you can describe a response for an impulse, a point-spread function, then you perform a Fourier transform, you get the optical transverse function. Normally, this is normalized, and then the modulus of the optical transfer function is the modulation transfer function. So these are alternative ways of looking at the response of the system. We are assuming, of course, a linear system and a shift invariant. Okay, now what do I mean by computational optical imaging? So we are used to perform imaging with the lens, okay? And that's how our eye essentially performs the imaging, although there is a complicated neural network behind the retina and the processing in the cortex, but essentially we have a lens. But imaging is not necessarily done in that way. Does not necessarily need to be done in that way, where you have a one-to-one correspondence. So from an object, we have a corresponding point on the image plane. That's what happens with the lens. But here, in general, we can have an object and we can change the illumination, for example. And that's called active illumination. If you project different patterns, sinusoidal patterns. You could also, if you have fluorescence, you could have different types of fluorescence shining different colors here. And then you are going to have waves going through the system, and instead of having a lens, you can add other things like ratings, holograms, face masks, and so on. And then you have a detector. Now in the detector, when you do this, you will not necessarily get an image, you get some measurements, and this is related to the prior talk. You get a measurement that is related to the object. It doesn't need to be a nice image that we can understand. Then you can perform some decoding or inversion or reconstruction and get an image. Now sometimes you don't want necessarily an image, you want a measurement, meaning that you might want to get some features of the object, not necessarily a nice optically appealing image for a human being. So for example, you might want to classify objects, you might want to detect objects, and so on. Now, what I represent here is a generalized measurement. Okay, so a measurement in this type of system is a projection of the multi-dimensional coherence function. So the way to represent the wave here, we can represent this if it's a complex, if it's a coherent light, we represent it with the complex amplitude. If it's incoherent, we use the intensity. But if it's partially coherent, we use the coherence function or the spectral density function. Now, how many dimensions does light have in the classic sense? Well, it doesn't have 2, doesn't have 3, doesn't have 4. It has 7 dimensions. Okay, because these are correlations between 3 coordinates in R1, 3 coordinates in R2, and frequency or time, depending on what representation you use. So ultimately, you want to project that, and this H is what we represent as a point spread function of the system. Again, it's multidimensional. And any measurement, even if you don't think about it, is going to be a projection or inner product of these two, and you get one measurement. Okay, so why do you complicate things if you can do it simple? You use a lens, right? Well, the main point is that by using this approach, you may capture information that is lost with the lens. Okay? So depending on the application, you might want to do this. And one typical example is tomography. Okay? Tomography can get 3-dimensional information which you cannot get with a regular image. Okay, so we're going to look at the problem of super resolution, but there are other applications of this concept. So the main question is this possible? Okay, and this is Abe, this is Rayleigh. Okay, those that first discuss in a numerical way the diffraction limit. And here, as you can see, we are asking, can we get the resolution in X and Z much smaller than this diffraction limit? And they look skeptical in this representation. So, in fact, it's possible, and the first proposal of such a system was here in the 90s, more than 15 years ago, by Stefan Hell. And in all these cases, if we look at the problem from a linear systems point of view, it's impossible. Okay, so there has to be some type of non-linearity in order to beat the diffraction limit. And people realized that for a long time, but finding the right way of doing it took some effort. Okay? And it's still a matter of research, as we're going to see. So the first method proposed was this, it's called stimulated emission depletion microscopy. Okay, so the idea is that you excite with a pulse of light. This is a scanning method. So you scan a spot. Okay. Now the key is that in addition to use a spot, to use this spot, say in the green, use another beam, scan, overlap with this one, in a way that this beam is, even though there is a plus here, because you illuminate the sample with both, the effective point spread function is going to be only appearing at the difference or in the center of this donut mold. Okay? And the idea here is to play with the fluorescence of there are fluorescent molecules or fluorescent dyes, and to play with the spectrum of those. Okay, so if we look at the spectrum here, what is going to happen is you're going to have an excitation to a higher level. We're assuming this simplified model. And then fluorescent means you have a transition to ground state. Okay? Now the idea is that this beam is going to generate stimulated emission, and so you're going to deplete in this area, where you illuminate with the red, you're going to deplete all the photons that could be emitted in that area, so you are only going to have fluorescence in the center. Now if you look here at the excitation spectrum of a typical helical molecule, and the emission spectrum. Okay, so here you use the excitation, which is this laser, and here you use the stimulated emission to deplete. Okay, and then you detect somewhere in between. Okay, so the main point here is that the effective point-space function is going to be much smaller than the diffraction limit. Okay, so how do you do this? You just illuminate with a quenching beam, which is this donut beam, and the fluorescent emission comes back generated by a smaller point-space function, which is much narrower than lambda divided by 2. And there have been many publications lately in the last 10 years showing super resolution. Okay, so you can, in particular, Stefan Hertz's group has demonstrated an order of magnitude, at least improvement in resolution using this technique. So that's, again, a scanning technique and requires two beam illumination. There is an alternative technique that was first demonstrated now 4 years ago, okay, almost simultaneously by 3 groups, which is called under the acronyms of PALM or STORM. So photoactivation, localization microscopy, or stochastic optical reconstruction microscopy. So the idea here is that when you have molecules emitting fluorescent light, if all these molecules are very close, you just see a blur, because all these blurs overlap, so you cannot distinguish them. Now, the idea here is to illuminate with some light and then excite these molecules. And so, at some point you're going to bleach these molecules, so it's not going to be any more emission, fluorescence emission from there. But then you excite with a different frequency, a different color, that is going to reactivate these molecules. And so they're going to meet, to be able to meet again, but only a few of them are going to be able to meet. And the way you control that is by the power of this second wavelength. So again, they are reactivated, and then you shine again, for example, with 514 nanometers, and you're going to see only a few spots. Okay, so the main idea is to have a sparse array of molecules emitting at a given time, and you control that by controlling the power and the color of the illuminated light. Okay, so you get 3 spots in this case. Now, you can find the exact position of each molecule, or very precise position, by finding, for example, the centroid. There are algorithms to estimate the position of each molecule. So now you know the position of these 3 molecules. You repeat the process with different 3 molecules, and so on. Okay? At the end, you can build an image of the position of all these molecules and get an image that looks has a super resolution. So the super resolution is achieved by a super-localization, or in other words, to be able to localize each molecule with a precision that is much better than the diffraction limit. Okay, so the fact that you can localize an object with a better precision than the diffraction limit is something that was originally proposed at least by Heisenberg many years ago. But the implementation for optical microscopy is only 4 years old. The key here is, again, to be able to have at any time a sparse array of molecules emitting. All these molecules are emitting and then in time you keep changing the molecules that are emitting at a given time. In general, there are 2 types of molecules that are photoactivatable, so they're going to emit and then bleach. So only once they're going to emit, and there are photo-switchable molecules that you can switch on and off stochastically. And that's the method that is used in STED. Okay, so there are many variations on this, depending on the molecules, the excitation wavelengths, power, and so on, but essentially all these are based on the same principle of having a sparse array of molecules and then randomly change that array. Okay, so and then you can compare with a traditional image, you gain resolution. And these are images from the Schwartz group at Harvard, showing conventional imaging, okay, and this type of stone palm imaging, where you can get point-by-point generated images with high resolution. Okay. So a different technique that is also very interesting is called saturated structured illumination microscopy. Was developed by Max Gustafsson, and this is based on the Moire effect. So the Moire effect is essentially using structured illumination. You illuminate the object with a sinusoidal grating, then you illuminate and then you are going to see some modulation of this grating, and then you compare with the original illumination, and you get fringes which have lower frequency, and the frequency of these fringes is at the difference between these two frequencies. Okay, so what do we gain here? We use high frequency images, gratings, to obtain low frequency variations. But these low frequency variations are originated in high frequency changes in the object. So this is similar to what is used in communication for bringing high frequencies to a lower frequency. Okay? So with this Moire technique, which is known for a long time, you can access, if these are the frequencies you can access with your classical imaging system, you can access the gray zone, the dark gray zones here. So you can access twice the frequency. Okay, you can, this is a Fourier plane, so you can extend the cutoff to twice the size of the frequency domain, which is good. You can improve resolution by a factor of 2. But if you use a nonlinear illumination, okay, nonlinear, so you use some nonlinear effect, you know that if you use nonlinear effects, you can generate higher harmonics. Okay? So you have this sinusoid is going to be now, it's not a sinusoid is going to have higher harmonics, it's going to be more like a square wave. So then you can generate higher harmonics in the spatial frequency domain, so you can access all these other circles. Okay? Now, you take this illumination pattern and rotate that pattern, and then you can generate all these other circles in the frequency space. And at the end, you can have in the frequency space a much larger domain and expand the resolution of the cutoff is going to be, for example, 5 times larger. Meaning you have 5 times the resolution. So this requires structural illumination, requires afterwards post-processing, and then sequentially projecting different patterns. Okay? If we go back to the prior technique, this is a wide field imaging. The stimulated emission depletion microscopy is a scanning technique. This is a wide field technique, meaning that you take images of a wide field of view. But takes time to generate an image. The same here. It takes time to generate this image because you need to project different patterns, but it's a wide field image. So to compare these techniques, the way Stefan Hell proposes is to look at the object and look at here B and A are molecules that are that have different fluorescence states. So the key is to be able to switch the state of these molecules. So B represents a dark state and A represents a fluorescent state. So in the STED microscopy, you use these 2 beams and you can bring the molecule to the fluorescent state only in the center of the nanomole, and then you scan, you are targeting specific location and build an image point by point. In the structural illumination, it's essentially the same, but you're generating lines on which you have molecules on, and thicker lines where you have molecules off, which is B. Okay? So this is what he calls targeted switching and readout. And then there is a stochastic switching, which is dependent on the power of the light you use, where the molecules at random appear emitting light, and this, which molecules emit at any time is random, stochastic. So the bottom line is, in order to get super resolution, you need to be able to switch on and off molecules, or some property of the matter. Okay, but those are the most popular or famous techniques, but there are other emerging techniques which I think are of interest. One of them uses time correlations. Okay, so how does this work? You have a set of emitters. Okay, quantum dots are used for this. So you have the emitters, and quantum dots blink. So they emit light, but they blink. So instead of taking just one image, you take a sequence of images. Okay? So for each quantum dot, you're going to get a big spot. And these two spots might overlap, but you take these spots over time. So because they are blinking at some time, at some point, you're going to have one, and at another point you're going to have two, at another point you're going to have the other one. So you get a movie here, a set of images, and for each pixel, you can think of a time signal, okay? So for each pixel, you get a time signal that is blinking. So that's your data acquisition. And then you perform a correlation. You perform a correlation, a second order correlation for each one of these pixels. And what you can see is that the effective point spread function, when you take the second order correlation, is that it is smaller. Okay? So instead of getting a spot like this, you get a spot that is reduced in width by a square root of 2. Okay, so this was proposed recently, last year, by this group at UCLA of Simon Rice. Okay, so this relies on the higher order statistics of light. So we are looking at the time sequence. So here you see, now you can take higher order correlations, and in fact it's calculated using something that's called illumination. But things work like this. If the original image will look like this, the second order correlation looks like that. So you see a smaller point square function. Fourth order looks narrower, and higher orders look even narrower. Now, one of the points that also the weaker quantum dots are going to become weaker, but you can choose which correlation order is better. And this is a wide field, again, but you need to scan in time. You need to take multiple images. And here you see the regular image after deconvolution, and then here you see with this, I will use the second order, right? And second order after deconvolution. Okay, so the key here is to look at the time variation of the signal, and then you can separate points that are closer to the diffraction limit. Another related technique that is also interesting looks at what is called the independent component analysis. So again, the idea is to take a movie, a time sequence of signals, and these algorithms are used to separate sources. Okay, so the idea is, if these are used, for example, if you are listening to two sounds, can you tell if they belong to the same source or different sources? And for that, you need to look at the statistical properties of this signal. And using this algorithm of independent component analysis, you can separate two signals. So you look at this sequence. If you integrate over this sequence, you get two spots. So here you can separate them or resolve. And these are the two independent components, and here a different color. This is from Heitzman group, who's now at Jena. And in this case, we see that if you look at the sun, it looks like there's only one source, or one quantum dot. But when you calculate the first two independent components, you get two. And so you can separate these two quantum dots even though they are very close, much closer than diffraction. If you had one quantum dot, one of the independent components will look like those. Okay? So you look at the independent components, and they are, if they look like a point source, that means you have two sources. If they look like noise, it means you have only one. Okay, so in this case, you can resolve blinking sources that are very close. Something similar has been used to look at the stars, for example. Okay? So you look at the statistics of the signal. Okay, so what happens with the third dimension? Well, all this, what I described so far is in 2 dimensions. If we now want to look at 3 dimensions, we are going to take the clues that we have for the visual system. So in this image, for example, we can tell, even though it's a 2-dimensional image, according to our experience, we can tell which objects are closer, right? We know that this cab is closer, and this one is far away. In part because this is bigger, and also in part because it's blurred, and due to the motion, because it's closer, it's going to appear blurred. So from the context, so this type of information is difficult to include in a computational system that is going to be automatic. Now there are other techniques. One of them is parallax, essentially having 2 cameras or 2 points of view. But this is difficult to implement in microscopy because normally you already have very high numerical aperture, so you cannot put 2 images there. You cannot fit 2 images. Now the other technique is focus and defocus. And this one is in fact very appropriate for microscopy because of the high numerical apertures, we have very strong defocusing. So remember our Z resolution was inversely proportional to the numerical aperture square. So high NA means we are going to have strong variations in defocus. So what we are looking here is ways to localize particles in 3 dimensions. And this is related to the methods called palm or stop. So the idea is to find the position of particles in 3 dimensions with very high precision. And here we are comparing 3 methods that have been proposed for that. One of them uses an astigmatic lens. So if you see a focus, a spot, that means that this particle is centered in Z. If it's elongated along Y, we know it's behind focus. If it's elongated along X, it's before focus. So by looking at the shape of the point spread function, we can tell the position in Z as well. A different technique is to use 2 images, similar to a technique used in machine vision called flipped from defocus. So in this case, you just take 2 images, but image in a different plane. So you're going to see one in focus and one out of focus. So they're going to change like here. So you have one out of focus, one in focus, or 2 in focus, or the opposite. So according to the relative size of these spots, you can tell if the object is behind or below focus. And the last technique uses the engineered point spread function, which I'm going to describe in the following slides. But essentially, it's a point spread function that instead of being elongated as we change the z location, it's going to generate a double helix. So as you move the point source back and forth, this is going to rotate. Okay? You're going to have two spots that rotate. Okay, now this 3D localization is important not only for PAM, it's important in other areas of biology, as I'm pretty sure Fiestun explained earlier. So you can look at for example, in flow cytometry, you can look at molecular dynamics, different biophysical experiments, or even for nanofabrication to track the position of microparticles. So, okay, so that was a review of things that the main methods are used for super resolution. So we know this is possible, so now we want to see how to improve and extend this to 3 dimensions. And as I said, we use this concept of point space function engineering in 3 dimensions. So now I'm going to talk a bit about this. So what we are talking here is to generate an arbitrary, as much as possible, distributions of light in a volume. Okay? So the analysis of this. Okay, let's say I have a phase mask that generates a given volume. It's very simple. You just use Parnell diffraction. Now, the synthesis is a bit more complicated. So if I tell you I want some distribution that generates a helix in space here, give me a phase mask that generates that. That's a bit more complicated. So ultimately, it leads to a constraint optimization problem. And the constraint is given by the wave equation. Okay? Whatever you're going to do here has to satisfy the wave equation. So there are a few methods to do this. And one of them is to impose these constraints in direct space. So essentially you say, here's the area, the volume where I want to impose constraints. I'm going to divide this in different planes. I'm going to impose the wave equation. The distance between these planes has to satisfy some sampling condition. And then I need to impose the technology constraints. For example, can I do a phase mask? Can I do an amplitude mask? What is the aperture? The resolution of this mask? The errors in the fabrication and so on. All that can be included here. And then, because not everything is possible, I need to set some hierarchy, okay, which is imposed by weights. Okay, so you use a weighted, this W are the weights that tells you what things are more important to satisfy. And then you impose some optimization and eventually try to find a solution using, we use these projection algorithms, but not necessarily, it's not the only way to do it. This is similar to Gershwin-Saxton or Gershwin-Papoulis algorithms that are known, but are more general in the sense that they have, you can impose constraints in multiple domains, and in fact they are older than the Gershwin-Papoulis algorithm. They were first proposed in the mathematics community in the 60s. So the idea is that each condition you want to impose on this wave is expressed as a mathematical constraint, and you impose sequentially all these constraints and repeat this continuously, and there are some, under certain conditions, these things converge. A bit better is to do it in parallel. So you impose the constraints on all these planes and all these conditions in parallel, and then take a weighted average. So you multiply by weight, take a weighted average, and repeat this process. And all these, you can also combine serial and parallel and so on, and things also converge. So this is an old example of this algorithm. Working to try to straighten a donut hole, which we saw is useful, for example, in STED, also in the particle trapping. So if you use a Gauss-Laguerre mode, this this donut model is going to diffract. You're going to have lower intensity here. And also the angle here of the notch is going to be wider. If you optimize on a given distance, to get a constant notch, you get something like this. And this satisfies the wave equation. So you can get a kind of donut model, but with a constant notch. I don't have here the image, but what you are giving up is the singular symmetry, which in most cases is not important. Okay, so you are essentially controlling diffraction with diffraction. So that's why we put non-expanding in quotes, because after a certain distance, these things are going to expand. Another method is to use a frequency domain. Essentially, just perform a three-dimensional Fourier transform and a projection onto one plane. It's conceptually easier, but in practice not as good. And the third method, which I think is interesting, is to use the modal domain. So the idea is to represent any beam as a superposition of modes, which we know we can do. So these modes could be, for example, Bessel beams, or it could be Gauss-Laguerre beams of higher order, or any other modal decomposition of the waveform. Okay, so now if we want to optimize this for a given task, we only need to find these coefficients. Okay, so we need to find these coefficients. How do we go about that? Well, it depends on the task. We're going to select different functions here, okay, different bases. For those that have a background in signal processing, there's always a best basis to represent a program. So, in particular, we are interested in looking at what we call propagation invariant wave fields. That is, waves that propagate and they self-image with rotation as they propagate. Okay, so you have a wave, after some distance you have the same pattern rotated, after some distance the same pattern rotated again. And in the middle you can have diffraction. But there are no lenses, okay? So there is imaging, self-imaging without lenses, but also with rotation. And for this problem, we use the Gauss-Laguerre basis, which is characterized by two numbers, m and n. So for the 0, model, it's the Gaussian, the elementary Gaussian. Higher m means you have a vortex of higher order. So you have a 0 in the center and a phase that goes 2 pi, or n equal to 1, or 4 pi, or 6 pi, and so on. And n is related to the number of lobes of this Gauss-Laguerre. So we represent this in a plane. The same way we will use the Fourier plane to represent each point of the Fourier plane is a different sinusoid. Each point in the Gauss-Laguerre model plane is one coefficient for this, represents one of these modes. So when I'm talking about this something, for example, to give an idea, here we have a realizable beam that has the shape of a cross. As it propagates, you get the same cross rotated 45 degrees, and then another 45 degrees, and so on. And here I'm going to show a simulation of how these things evolves. You see, you get a cross, and then it's diffracted, but after some distance, it appears again. So this is similar to the Talbot effect, but the main difference is that we have a finite energy. In the Talbot effect, you need to have an infinite rating, where here you have only you have a finite energy. And in fact, it's related to the Talbot effect, as I'm going to show in the following slides. So, how do we find these waves? Again, we can find a condition that says that any wave that has this property of self-imaging with rotation has modes that lie on parallel lines. Okay? So this line has to be at the same distance. If you select modes on parallel lines, you get this type of waves. And special cases, so this is a mathematical formulation of just that statement. And special cases are the rotator self-imaging, which is what I show. The Eigen-Fourier transform functions, which is a function that is, you have a certain distribution, and in the far field, you get the same distribution. The rotating beams or helical beams, the Talbot effect, Bessel beams, and the generalized propagation invariant beams are all included in this correlation. Okay? They're all special cases. So the Eigen-Fourier function, for example, is a function that the Fourier transform gives you the same function times a constant. Okay? And can be derived from this. It corresponds to parallel lines, horizontal lines. Now the Bessel beams are also part of this, and to do that you need to take the limit of the Gauss-Levier beam when the waist is infinite, and look at the central location. That means close to this. This should be Z0, so close to the waist, and also a large n relative to m. You need to look at the Parnell regime, and you get the Bessel beams, and so all the Bessel beams in the properties of the self-imaging with Bessel beams and rotating beams are derived from the same condition. One interesting thing is that the condition is necessary and sufficient, which is a mathematical statement. What does it mean? That any distribution that has this property can be described as that formula, and that formula describes all the distributions that have this property. So all are covered there. As I said, they have finite energy, so you can generate these beams as accurately as possible as you want. So because the same way you can generate a Gaussian as accurately as you want, right? Because the Gaussian has finite energy, so you can put like 99.999% of the energy inside your aperture and get it as close as you want. As opposed to Bessel beams, which are always, when you use an aperture, we're going to eliminate infinite energy. Bessel beams have infinite energy. The phase map is preserved. That means, except for a quadratic phase, here we have an example. This is the phase. You see 1, 2, 3, 4 dislocation. As this rotates, it's the same dislocations with the addition of a quadratic phase. So that's a property. Okay, the rotating beams are interesting and a very important case, as we are going to see. And they correspond to modes laying on one line. So you take any modes on one straight line at any angle, and you get a rotating distribution. Okay? So you take a different line, and you get something different. Okay? How are we going with the time?
I think that if we want to take a break, it's quite
No, this wasn't the slide where I was trying to make a break.
Ah.
Okay, so let me summarize so far. We've seen methods for super resolution, and then I claim that using the shaping the point space function, we can improve some of these methods in 3D. And I show how to generate three-dimensional point space functions. Okay? And the helical beams are one case of these three-dimensional point space functions, which I'm going to use in the following part of the talk. Thank you.
We have to rest for 5 minutes.